Hello, everyone. My name is Rick Win. I'm a research fellow in the Division of Material Science Research at Model 3D. Today, I'm very happy to present our published innovations regarding digital twin. These slides give you the outline of today's presentations. First, I will introduce how to create a digital twin from a capillary rheometer. I will demonstrate the advantages of using the material digital twin by giving two case studies. The first one will concern the viscosity at a very high shear rate. We will demonstrate how to take into account the high temperature rises during the measurement. In the second case, we will discuss extensional rheology in a high contraction ratio flow. Overall, the idea is to retrieve reliable viscosity functions that can be used in modeling simulations involving very complex geometries or at very high shear rates. Creating a digital capillary rheometer. I believe most of you are familiar with how to determine shear viscosity from a capillary rheometer. The definition of viscosity is shown here. It is wall shear stress divided by the wall shear rate. The wall shear stress can be determined from the pressure drop through the capillary die. The shear rate is calculated from the flow rate Q through the tube. As you can see, each curve through the data points represents viscosities at a constant temperature, but at a different shear rates. To be more specific, we gradually increase the piston velocity from a low velocity to a high velocity. By using the Newton's law of viscosity, we can construct an isothermal viscosity curve, which can be used for simulations. This is the flow chart detailing the procedures.